It's a great pleasure to be talking about my friend. I think we are into 39th year now of being together in various places. So this is more of a recollection, an anecdotal account of all the things that we did. There will be something technical, but not too much. So I just want to go through various stages. This is cumulative. We started as friends, then we became friends and collaborators, and then friends, collaborators, and also activists. Shankar doesn't think so, but there was a bit of activism. So I want to mention all the three briefly in the next half hour or so, recall various incidents. So I met Shankar first in 1981. We were hostel mates in TIFR. I don't remember exactly our first meeting, but what I remember very well is that he and another student, Sanjay Jain, they started working together on a problem in lattice models. They were looking at some equivalence of Bravais lattice and Susskind lattice with Avinash. All three students working together. Formally, he was, of course, student of Divakaran, but that is where he started. But he was quite broad even then. He had a lot of experiments going on around the same time. One was on circadian rhythm. He tried why a day should be 24 hours, have a sleep cycle and wake up cycle which is 36 hours. So on some days we would see him walking for breakfast with us. On some days he would be walking for breakfast at dinner time, and all this, a lot of fun we had in the hostel. And I think Jam knows, Sampath Kumaran, he is here. All these people know about these things. Around this time, little later, I think he wrote this very highly cited paper, Nambu Journalist Neotype Effective Lagrangian Anomalies and Nonlinear Lagrangian of Low Energy, Largen QCD, with Avinash Dar and Spenta Vadia. I think this formed quite a bit of his thesis. Somewhere around 83, I left, and he continued for his PhD. And then again, in 86 June, I came to IMSC. I joined IMSC. He also came here as a postdoc. So again we met, and this time we seriously started working together. And he was an expert in SCORM model. I was working on deform models. So together we started working on what's called as a deform SCORM model. And we were also joined by a very young student who had just come at that time, Indumati. Actually, we did this work, but then we found that it had already been done. It had some nice features, so we didn't pursue it further. Then, during this time, of course, our personal relations was pretty strong, and here is Shankar congratulating an young couple. You can guess who they are. This was Shankar, who came to my wedding in Bangalore. It was called the DAE sponsored wedding because it so happened that the High Energy Physics Symposium was 2 days later in Mysore. So the whole gang of students, including Shankar, arrived at Bangalore, attended my wedding, and then went to DAE symposium, including me. And we were all paid by TIFR for our journey. So that's why it was called as DAE sponsored wedding. And then, of course, after coming back, I moved to one of the apartments, so the apartment became a kind of watering hole for all the students. And you can see Shankar chilling out in our apartment in TIFR. There are many pictures like this. In fact, I have pictures of Jam also sitting in the apartment having tea or something else. So then Shankar left IMSC after his postdoc, and then he was in Kanpur IIT as a postdoc, and then he came back to IMSC and joined IMSC in 1991 as faculty. And in 1993, he moved to the penthouse in the main building, in the IMSC main building, and we began our collaboration on exclusion statistics. I became a student of Shankar during this collaboration, learning all the time. He taught me a lot of things. I'll tell you a little bit about that. But during this time, we also had enough time for other pursuits, like having a symposium. You can see Shankar conducting it, or going for picnics with students and things like that. Those were the days when we were a small group of people. So all our activities was together, the faculty, students, everybody would go together, and there was a lot more interaction between students and the faculty. Of course, we were all young, probably a few years older than the students themselves. So it was very nice. We had a very congenial atmosphere and a lot of interaction. So what is this exclusion statistics that I learned from Shankar? This started with a paper in 1991 by Haldane. It's a seminal paper wherein this paper was written in 1991, and up to about 1993 nobody had noticed that paper very much except Canright and Johnson, who wrote a very paper which nobody could understand about fractionalization of Hilbert space dimension. So the basic idea of Haldane here is that suppose you have n identical particle system and you freeze n minus 1 coordinates, and this expand this psi in the complete set of single particle states spanned by this psi, and call it dn. This is the dimension of the single particle space in the presence of n minus 1 others. It's embedded in this. So as the number of particles change, how does this embedded single particle space dn change? So generalizing from Bose and Fermi, Haldane wrote an explicit relation where this changes according to minus g times delta n. Now you can see that when g is equal to 1, the available single particle space is reduced by 1 unit if you increase the number of particles by 1. And if they are bosons, of course, nothing changes. And this g in general can be fractional. So state counting with these. So for example, if you have fermions, let's say there are d states available, and for the first particle all d states are available. For the second particle, since one of them is already there, it's d minus 1. For the third particle, it's d minus 2. For bosons, of course, all the d states are available. There's no exclusion for bosons. So you can write, this slide is actually from one of the slides which Shankar wrote for his colloquium in TIFR. I just took it from there. So this, for fermion, the single particle space can be written in this form. For bosons, of course, it is d. So for arbitrary g, arbitrary blocking of these states, you can write it in terms of d minus g into n minus 1, where g is a statistical parameter which is equal to 0 or 1 for bosons and fermions. But it could be, let us keep it arbitrary. That was Haldane's idea. Now from this you can go into constructing the n particle dimension for fermions. This is there in any statistical mechanics book. For fermions it is this, for bosons it is this. So you can generalize it, and for blocking of geons, it is dn of g plus n minus 1. In fact, they are identical except that the single particle space dimension assumes different forms for bosons, fermions, and now for geons. Of course, in this case, g has to be rational for dn to be an integer. So here comes the masterstroke of Shankar. Quantum theories must be based on observables. We don't observe Hilbert space dimension. So how do you go? So he said, let's take dn. The counting of states can be done using the partition function in the limit t going to infinity. When beta goes to 0, this simply counts all the states, and that is simply the n particle state. This is a canonical partition function. So then you can expand this dn, replace it in this limit by the partition function, and you can extract the statistical parameter which is given by half minus g, limit of beta going to 0, in terms of these partition functions z1, zn, and z1 to the power n. The constant c depends on the density of states or dimension. And for n is equal to 2, in fact, this is precisely the definition of the second virial coefficient which figures in the equation of state. This was our first paper. And you can, of course, obtain the distribution function also. For Bose gas, we know what it is. G is equal to 0. For Fermi gas, it's G is equal to 1. For the exclusion statistics gas, you can say this is of this form, where this W is a function which is a solution of the nonlinear algebraic equation of this form. And incidentally, we found that this solution of this nonlinear algebraic equation is given as an infinite series in one of the Ramanujan's last notebooks. And one of the things that we did in our paper when we wrote this is that we called this as exclusion statistics, because normally quantum statistics is defined in terms of exchange of particles. Whereas here you are defining the quantum statistics in terms of exclusion. So in our paper, to contrast it with exchange statistics, we called it as exclusion statistics. And in particular for arbitrary G, we called it as fractional exclusion statistics. And since that was the first time it appeared, that name has stuck for this field. In fact, almost all the papers since then refer to it as exclusion statistics or fractional exclusion statistics, a name given by us. And so you can now do thermodynamics. So it's really physical. So from counting of states, the Hilbert space dimension, we have come to something which is really physical. So here is a summary. Unlike anyons, the exchange anyons, which is specific to two space dimensions, where the generalization of statistics can be done through exchange only in two space dimension, exclusion statistics is defined for any space dimension. At 0 temperature, you can check the occupancy is 1 over G. So when G is equal to 1, the occupancy is 1, which is fermions. When G is equal to 0, it can be arbitrary. And at finite temperature, it's given by what the expression I just showed in the previous slide. It nicely interpolates between Bose and Fermi statistics. Statistical mechanics of geons is well studied and understood. How does it arise in physical systems? So we illustrated its origin using models in one dimension. There's a famous model called as the Calogero-Sutherland model, and Luttinger liquid. And later, with other collaborators in 2 dimensions, we showed that it can occur with short range interaction, and in 3 dimensions, probably cold atoms at unitarity, where we make contact with experiments. And this, in fact, this paper that where we wrote down the equation of state appeared as news in Nature. John Maddox, who is the editor, wrote an editorial in News and Views on this paper. This is a short extract. Of course, he said we are from University of Madras. It's okay, he made a mistake. So in the 90s, our collaborations continued. This is the first paper which I just described, where the basic idea started with Shankar's generalization to infinite dimensional spaces. Then we wrote a paper on the thermodynamics of a one-dimensional ideal gas with fractional statistics, where we looked at the realization of this exclusion statistics. And then exclusion statistics and strongly correlated electron system. This was actually based on a talk given by Shankar in IMSC in one international conference. Then we did something which is nice, which is exclusion statistics, a resolution of the problem of negative weights. Wilczek and Nayak pointed out immediately after our papers came, our paper and Wu's paper came, is that if you assign probabilities for individual states, then it turns out that for some G, it always becomes negative. The weight becomes negative. And therefore, you cannot interpret probabilities for individual states in terms of the Boltzmann weights. So we showed that this probability, this negative weights negative probability problem can be solved by looking at a generalization of the Pauli exclusion principle, which not only acts on an individual state, but it acts across states. So once you take that into account, there is an overcounting problem. To correct the overcounting problem, these negative probabilities occur. And if you don't do that overcounting, and if you take this generalized Pauli principle which acts across states, then the negative probability problem doesn't arise. And this we solved in this paper. We also wrote a couple of other papers in the 90s. There was something which we extended to Carroll bags. And this is a different paper where with our student we worked out the shell effects in quantum dots. It's different from this thing. So all this and more is in this IMSC report number 120, which was actually written as a book. Now it is available online. And the first 5 chapters are based on the work which Shankar and I did. And then rest of it is something which I did with other people. So this, even though it is not published as a book, but it's available online, this, a lot of people write to us about this book and say, is it published? I mean, just to quote, I mean, how to quote, and such questions are asked. But nevertheless, I think this has become a very useful thing. So after that book summarizes all the work that we have done in physics, but our collaboration continued and it became something else completely after 1998 Pokhran explosion. So Shankar, I, and many people in this institute, in fact, large number of people from this institute, got involved in the issue of nuclear weapons and how it threatens peace. And in that context, we went into the literature. We first wrote a booklet which summarized all the facts about nuclear weapons, just for information. People should be educated before talking about various things. So in order to do that, first we brought out a booklet called Facts About Nuclear Weapons. And then we thought we will write a booklet. In fact, it turned out to be much larger than a booklet. It's almost 100 pages, about how the tragedy of Hiroshima and Nagasaki happened. So in fact, in this, which we compiled and edited using various sources, we started with how the decision to drop nuclear bombs on Hiroshima and Nagasaki was taken. See, it's a very interesting thing that the most important decision about the dropping of the weapons was done by the scientists. It's not the military. In fact, we show and quote that in fact military was opposed to use of these weapons of mass destruction because it's not the military ethics to use such weapons. There was a big debate about it. And the scientists, on the other hand, thought that they went into all intricate details. How to see the effect, how to maximize the effect, what is the most effective way of using this bomb. It was science for them. They had done this, they had created these monsters, and they wanted to study what the effects are. So in this book, we go through the making of the decision and the actual act of dropping the weapons, what the people who actually did that felt, what they said at that time. And then there is a third section in this, wherein we recount the interviews, what people who are affected by these weapons said, the effects of nuclear weapons. Now, after this, for almost 10 years or a little more, every year we used to have a peace stall in Gandhi Mandapam. On October 2nd, Gandhi Jayanti, there used to be an exhibition here next to IIT in the Gandhi Mandapam. And there we invariably got a stall. We had a group, small group of Indian scientists against nuclear weapons, which became part of a much larger group for movement for peace, which had journalists and others. And they used to get this stall, and then along with Shankar and many others from this institute, we would put posters, messages, and explain to people who come there, precisely what the effect of all these things are. It was called a peace stall. And in fact, if there was anything that was closest to a Gandhian ideology, it was this stall. And we conducted this for almost 10, 11 years. And I think in 2009 we stopped. And this is one collaboration which we ran for a very long time. But we have another project coming, which we have just discussed, and now it is possible because Mr. Veerappan is not there. And traveling the course of Kaveri River, and perhaps, at least for me, produce a photo essay. This we have been talking for a long time. Maybe next year we will do that. We want to start from the origins, come all the way, travel the course of the river till the sea, and then we want to understand a lot of things. And of course, for Shankar, this is a small problem because he wants to understand a lot of other things. He went into tsunami, studying tsunami, then glaciers, and now he's interested in climate change. So what I have been involved in his activities is a very small part of his broad range of activities. And in fact, after when we were writing that book, he said that now this kind of physics is not any more interesting because there is no connection to reality. He wanted to do things which are more relevant and which are more real. And that's how he went into tsunami and then this glacier studies. And it's huge. So from circadian rhythm experiments all the way up to glaciers, there's a huge canvas in which Shankar has been involved. And I'm very happy that I have been a part of at least a small part of this canvas. I have traveled with him. So thank you, Shankar, for the friendship and the joy of working with you. It has been great fun. Thank you very much.